Okay, so picture this, a massive grid of random numbers. And hidden somewhere inside is a perfect little puzzle, a magic square. Now, you or I might spot that pattern with a little intuition, a little luck. But how do you teach a computer to find it? Well, today, we're cracking that exact code.
And that's the big question, right? We humans are great at spotting patterns. A computer, on the other hand, needs a concrete step-by-step plan. So how do we turn that gut feeling, that human intuition, into a cold, hard algorithm? Let's dive in. First things first, we need to know the rules of the game. A 3x3 magic square is actually pretty simple. It has two very strict rules. Rule 1, it's got to use every single number from 1 to 9, and only once, no repeats. And Rule 2, the magic part, every row, every column, and yep, both of the main diagonals have to add up to the exact same number, 15. Let's see our real one in action. Look at that top row. 8 plus 1 plus 6, that's 15. The middle column, 1 plus 5 plus 9, also 15. What about the diagonal? From the top left to the bottom right, 8, 5, 2, you guessed it, 15. Every single line adds up perfectly. This is the treasure our little algorithm is trying to hunt down.
So, how on earth does a computer search for this pattern inside a much, much bigger grid of numbers? It doesn't guess. It doesn't have intuition. It uses a beautifully simple and methodical plan called the sliding window strategy.
Think of it like this. You have a 3x3 magnifying glass, and you place it right at the top left corner of the big grid. The computer looks inside that window and asks one question: is this a magic square? Then it just slides the window one spot to the right and asks again. It does this all the way across the row, then moves down one line and starts again. It's methodical, it's thorough, and it is guaranteed not to miss a thing.
Okay, so we keep saying the computer checks if a square is magic, but what does that actually mean? It's not a fuzzy feeling. The algorithm has a very specific, totally non-negotiable checklist that it runs through for every single window.
It really boils down to this super strict two-part test. First, the program makes sure that the 9 numbers inside its window are in fact the digits 1 through 9. No duplicates, no numbers like 12 or 0. If that checks out, it moves on to the hard part. It calculates all 8 sums, 3 rows, 3 columns, 2 diagonals, to see if every last one of them equals 15. So it starts methodically, right? It looks at the top row. It adds the 3 numbers. Do they equal 15? If they do, great, it keeps going. But if they don't, the check fails right then and there. The algorithm doesn't waste another nanosecond on this square and just slides the window over to the next spot.
And it just keeps going. It does the same thing for every single row, and then for every single column. It's what you might call a brute force approach, but hey, it's incredibly thorough. In total, it has to get 8 yeses for all 8 sums.
And last but not least, it checks the 2 diagonals. It's only when all 8 of these sum checks pass, and the first check for the numbers 1 through 9 passes, that the algorithm finally raises its hand and says, "Hey, I found one. I found a magic square." Phew. Okay, checking 8 different sums for every single possible square, that sounds exhausting, right? And it is. But what if there was a secret shortcut, a clever trick to throw out a square almost instantly?
This is where the real cleverness of programming comes in. I mean, think about it. Is there one single thing, one property that all true magic squares share that we could check for first? Because if a square doesn't have that property, we could just toss it out immediately without doing all that math.
Well, it turns out there is one single number that acts as a key to the entire puzzle, and that number is 5.
Here's the magic trick, and it's pure math. It's a proven property that for any 3x3 magic square that uses the numbers 1 through 9, the number in the dead center has to be a 5. No exceptions. Why? Because that center spot is part of 4 different lines that all have to add up to 15, the middle row, the middle column, and both diagonals. Its unique position makes it the one and only number that can balance the whole grid. It's the anchor. And that right there is the brilliant optimization. Before checking a single sum, before even verifying all the numbers are there, the algorithm takes one quick peek at the center square in the window. If that number isn't a 5, it's an instant nope. It doesn't bother with any of the other checks and immediately slides the window over. This saves a massive amount of time and effort.
So, we've got our strategy, we've got our slick shortcut. But in the world of computer science, you always got to ask the big question: how good is this solution really? Is it actually efficient? We usually measure this in 2 key ways. First, there's time complexity. That basically asks, if our grid gets way bigger, how much longer will this take?
Then there's space complexity, which asks how much extra computer memory does this whole process need to run?
And here's the final verdict. The time complexity is what we call OR times C. All that means in plain English is that the runtime grows in a very predictable direct line with the size of the grid. If you double the cells, you roughly double the time. It's super efficient. But even better is the space complexity. It's O1, or constant. This is awesome. It means our algorithm uses a tiny, fixed amount of memory, whether the grid has 100 cells or 100 million. It's incredibly lean.
So when you boil it all down, this whole sliding window idea is way bigger than just finding magic squares. It's a fundamental concept in computer science. It's used for things like image processing, to find faces in a photo, or in analyzing financial data to spot trends in stock prices. It really makes you wonder, what other huge, complicated problems could we solve just by looking at them through a small, simple sliding window?